Hi to all. In the previous classes, we started Magnetostatics. But orally, if you teach, then you can't understand. And if you prepare entire chapter wise, then you can easily understand, you can easily score the marks. Coming to magnetostatics, as I told you previously, the study of charges which are at rest is known as electrostatics. It is discussed in Unit 1 and 2. Now coming to magnetostatics, the study of charges which are in motion is called magnetostatics. When the charges are in motion, they produce magnetic field. Hence, we go for magnetostatics. The motion of charges is called current. Due to the current flow in conductor produces a magnetic field. According to whenever current flows through magnetic field, according to thumb rule, right hand thumb rule, the current direction, if it is like this, then magnetic field, the curled fingers indicates the magnetic field direction. Do you know that? What is magnetic field? Everybody knows that. The magnetic field, the space around a magnet which experiences a force on other magnet is called magnetic field. Suppose if you consider a magnet, if you provide another magnet, it experiences a force. Magnetic flux density, you know that the total number of flux lines divided by total area gives the magnetic flux density, and it is denoted by B bar. It is the ratio of total flux to total area. Why I am telling this entire chapter? Because you can understand easily. If you go for any one of the topic, you can't understand the previous basics. Hence, preparation of entire chapter gives rise to clear understanding. As the flux density is B equal to phi by A, we can write B equal to d phi by ds also. B equal to d phi by ds, where S is the surface area. Magnetic flux is a scalar. Similar to electric flux is a scalar, electric flux density is a vector. Magnetic flux density is a vector. Previously what we told, the electric flux density and magnetic flux density. The letter to indicate magnetic flux density, you know that B, whereas electric flux density is d bar. B equal to d phi by ds an, where the units of B is Weber per meter square. What is another unit for Weber per meter square is Tesla, where an is the unit vector. B can be represented, here we have to represent B equal to phi by A. From this we obtain B equal to d phi by ds an, where an is the unit vector normal to the surface. N stands for normal to the surface. Suppose the flux density B can be represented by normal to the surface. Therefore, phi equal to, we can represent from this equation, phi equal to surface integral B dot ds. Surface integral B dot ds we can write. From Gauss law, we know that psi equal to Q equal to surface integral D dot ds. Gauss law చదివేటప్పుడు మనకు తెలిసింది కదా, psi equal to Q equal to surface integral D dot ds. Similarly, psi ప్లేస్లో మనం phi పెట్టాలి. Phi పెట్టచ్చు. We can replace psi with phi because it's a magnetostatics we are studying. That is phi equal to surface integral B dot ds we can represent. Therefore, phi equal to surface integral B means d phi by ds we can replace, we can cancel each other, ds and ds. Therefore, phi equal to surface integral d phi, we can get total phi. I understand this. We can write in different manner. B equal to d phi by ds also equal to B equal to phi by A. Therefore, phi equal to surface integral B dot ds we can write. We can't write. Shall we write or not? Phi equal to surface integral d phi by ds. Yes, we can write. Because of phi equal to surface integral B dot ds, that equal to B, we can replace d phi by ds. If your ds get cancelled, hence d phi will come. If you integrate over the surface, if you integrate the surface d phi, then you will get phi. Integration of d phi gives over a surface gives phi. Similarly, the definition of magnetic field strength, H bar. H is given by mmf by length. mmf by length is known as H. Magnetic field strength or magnetic field intensity, mmf by length. mmf equal to ni by total length. The force experienced by unit north pole in the magnetic field is called magnetic field intensity. It is the measure of strongness or weakness of the magnetic field. I already told you in the last class. A brief introduction about unit 3. Already we made a video. That is the explanation without any notes. Now, to understand clearly, we prepared the notes and represented in the a good manner that can be understood to you. The another topic is B and H, how they can be related. D equal to epsilon E, we know that. D equal to epsilon E in first unit we studied. D bar equal to epsilon E, that is electric flux density is proportional to electric field intensity. Similarly, we can represent B equal to mu H, that already everybody knows, where mu is known as permeability, not permittivity. The retaining power of magnet is known as permeability, that equal to mu naught mu r. Mu naught is absolute permeability, that is 4 pi into 10 power minus 7. We have to remember the value of absolute permeability, 4 pi into 10 power minus 7 Henry per meter, whereas mu r is relative permeability, mu r equal to 1 for air. Now we go for the new topic, Biosavers Law, that you studied previously in 10 plus 2, that is 12 plus, you studied that Biosavers Law. The Biosavers Law used to find what is the purpose of Biosavers Law? To find the magnetic field intensity. Magnetic field intensity in the sense H bar. To find H bar we require Biosavers Law. If you know H, you can calculate B, that is magnetic flux density, by the use of relation B equal to mu H. By this use we can calculate. The Biosavers Law you studied in physics in 12th standard. It states that magnetic field intensity dH at any point P, at any point. Suppose a current carrying a current is carried out by that conductor, a current I produces a magnetic field. At any point you can consider the dH is proportional to, the Biosavers Law states that the magnetic field intensity dH at any point P is similar to Coulomb's law. How we define Coulomb's law in electromagnetics? It is directly proportional to force. Similarly, it is proportional to the product of I into dl. It states that magnetic field intensity dH or H at any point P is proportional to the product of I into dl. The sign of the angle between the element and joining the point P. It is also depends on I dl sin theta. It is proportional to, dH is proportional to I dl sin theta and inversely proportional to square of the distance at point P and current carrying element. It is inversely proportional to square of the distance. In Coulomb's law what we say that same, but in Biosavers Law, dH here in Coulomb's law force is proportional to Q1 and Q2 divided by it is inversely proportional to square of the distance 1 by r square. That is regarding Coulomb's law. But here it is Biosavers Law. The Biosavers Law states that, once again we have to remember Biosavers Law ఏం చెప్తుందంటే magnetic field intensity H bar or dH bar at any point is proportional to the product of ideal sin theta. The product of angle between angle of the point P and the current flows through conductor and differential length dl, ideal sin theta, and inversely proportional to square of the distance between the point P and current carrying element that is required. It is inversely proportional to square of the distance between the point P and current carrying element. Suppose a current is moving in this conductor I. A small differential length we consider, that is dl. A small differential length, suppose L is the length of the conductor. A point P is located. At this point P, if you join the line joining that point P is R12, and the dH is proportional to ideal sin theta divided by R12 square. If you remove the proportionality, you know that dH, if you remove the proportionality, constant will come, where constant is known as 1 by 4 pi. 1 by 4 pi, it is the constant is dH equal to k into ideal sin theta by 4 R12 square. That is R12 means the distance vector it is. From the point P to DL, where what is the distance? That is IDL sine theta by R12 square. I understand this. Biosavers law, how can we apply? A simple Biosavers law is it is directly proportional to ID, the current flowing the element, and differential length and angle of the point, and inversely proportional to square of the distance from the point P and current carrying element wherever the current is flowing. Therefore, we can write dH bar, that is magnetic field intensity dH bar is equal to IDL sine theta by 4 pi R12 square, because K we can write as 1 by 4 pi. IDL sine theta by 4 pi. It is the formula to calculate magnetic field intensity at any point P. In vector form, according to Coulomb's law, in vector form we derived. In vector form dH bar equal to sin theta will come in cross product only. Sin theta ఎక్కడ వస్తుంది? క్రాస్ ప్రొడక్ట్లో మాత్రం వస్తుంది కదా. ఐడియల్ sin theta, you can replace IDL sin theta with IDL into IDL cross AR12. IDL cross AR12 by 4 pi R12 square we can write. Ampere turns meter square. H bar can be written as ampere turns per meter square. The units of H bar, magnetic field intensity, can be given by ampere turns per meter square. What is the application? You up to now you studied that H bar H equal to IDL by 4 pi r square, dH2 equal to IDL1 AR1 by 4 pi R12 square. The formula is dH2, if you want to calculate, IDL1 into AR12 4 pi R12 square. Now we go for applications of Biosavers law. That is very important. Give any applications, give any 4 applications of Biosavers law. That interview questions or competitive point of view examination questions. It is used to find magnetic field intensity. That is the purpose. H bar is known as magnetic field intensity or magnetic field strength. MFD, it is simply we can write magnetic field density, or also it is magnetic field intensity. ఇంకో విధంగా ఏం చెప్పచ్చు అంటే magnetic field density, magnetic flux density కాదు, magnetic field density. The main applications of Biosavers law is to find magnetic flux density, magnetic field density or magnetic field intensity, H bar, to calculate. Where we have to calculate, how many ways we can calculate H bar. Suppose the standard conductor having finite length. Suppose a standard conductor having length L, we can calculate a point P. At point P, what is the magnetic field intensity? Suppose if the conductor is infinite length, we can calculate magnetic field intensity. MFI at a point due to circular loop. Suppose the loop of the conductor in the form of loop, we can calculate magnetic field density or magnetic field intensity at that point. Standard circular conductor having infinite length also, MFI at a point P due to circular loop, we can use the Biosavers law to calculate only H bar. If you calculate H bar at a point P, what is the magnetic flux density B bar, we can easily calculate, because B equal to mu H. H equal to B divided by mu, if you can calculate magnetic flux density also by using due to circular loop. To find magnetic field intensity at the center of the square loop, so many ways we can use the Biosavers law to calculate H bar. To find magnetic field intensity at any point due to solenoid of infinite length and finite length. By the study of all these applications, the chapter will be closed. By the study of all these applications, the entire chapter related. Okay, first of all, we have to understand what is Biosavers law. Simply, we can write Biosavers law as in the form of Coulomb's law. The magnetic field intensity H bar is proportional to IDL sine theta and inversely proportional to the square of the distance. Hence, the inversely proportionality, if you remove, then a constant will come, that is 1 by 4 pi. Now, first we go for magnetic field intensity due to a standard conductor having finite length. Magnetic field intensity due to a standard conductor having finite length if you apply the Biosavers law. How we are applying the Biosavers law to solve this type of derivations? We have to remember. ఫస్ట్ మనకు బయోసేవర్స్లో తెలిస్తేనే ఈ మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ డ్యూ టు స్టాండర్డ్ కండక్టర్ దట్ ఈస్ ద ఫస్ట్ అప్లికేషన్, సెకండ్ అప్లికేషన్ అండ్ ఫిఫ్త్ అప్లికేషన్. ఇఫ్ యూ స్టడీ ఫిఫ్త్ వన్ ఆల్సో, then anyone will come to find the H bar in examinations. Magnetic field intensity due to standard conductor having finite length. Finite length in a sense, what is this? Finite length means some length. Infinite length means it is a very large length that cannot be found. Consider a conductor, a finite conductor. We have to consider a finite conductor. L means some length, it people, not infinite. Infinite means L is infinite means that is a very large. Similar to Coulomb's law, how we applied the same principle we are also using by Biosavers law. Consider a conductor of finite length L placed along z-axis in a Cartesian coordinate system. In this diagram you can see x, y, z axis, it is y axis, it is x axis, it is z axis. X, y, z axis. Consider a conductor of infinite length. L is the conductor length. That is the conductor length L is placed along z axis. Now the current flows through this conductor is I. Assume that I current is flowing through the rest. Hence it produces a magnetic field. What is the point? At point P, what is the magnetic field intensity? We are applying Biosavers law. If you understand Biosavers law, it is very easy. ఈ కండక్టర్ జెడ్ యాక్సిస్లో ఉందనుకుంటున్నాం, ఎందుకంటే ముందు కూడా మనం కూలమ్స్లో కూడా యూజ్ చేసి కనుక్కున్నాం. బట్ అక్కడ మనం ఏం కనుక్కున్నాం? ఫోర్స్ కనుక్కున్నాం. ఇక్కడ మ్యాగ్నెటిక్ ఫీల్డ్ స్ట్రెంత్ అనుకుంటున్నాం. మ్యాగ్నెటిక్ ఫీల్డ్ స్ట్రెంత్ ఈజ్ రిలేటెడ్ టు స్ట్రాంగ్నెస్, వీక్నెస్ ఆఫ్ ఫోర్స్, మ్యాగ్నెటిక్ ఫోర్స్. ఓకే, let us assume that a small portion dl is the small portion and the angle making with the point P is theta and remaining angle is alpha 2 and this angle is alpha 1. The point P is located. The angle making with the conductor, assume that the conductor is at 0 condition, that is origin 0 it is. Now the height of the conductor from the top is z dash minus z it is. This remaining length will be z dash minus z. Are you understand this diagram? You can see clearly. ఒక కండక్టర్ ఎల్ లెంత్ ఉంది అనుకున్నాం ఫస్ట్, అది జెడ్ యాక్సిస్లో ఉంది కాబట్టి అజ్యూమ్ దట్ ఇట్ ఈస్ ఎ జెడ్ యాక్సిస్. A small portion length dl we assume. A point P is located at somewhere on x-axis, y-axis. Assume that the angle making with theta is theta because the dh is proportional to sin theta. The angle making with the point P at an angle theta. Now the height of the point dl from the top is z. From the top is z. Assume that it is z dash. Total height from the origin. Total height from the origin is z dash. Z dash minus z is the remaining height. Z dash minus z because the total conductor lied along z axis. Along z axis లో ఉంది. 0 నుంచి పైన వాళ్ళకి వెళ్ళేది z dash. అదే కిందికి వెళ్తే మైనస్ z dash it is minus z dash. Now making angle with the theta alpha 1 is the angle and this is remaining angle is alpha 2. Assume that. According to Biosavers law, dh bar equal to ideal sin theta by 4 pi r square. We can write ideal sin theta by 4 pi r square, where r is the distance. Where is r? The distance from the origin to the point P. The same thing here we explain. Let the conductor carrying a current I and it is required to find magnetic field intensity at point P. Our motto is to find magnetic field intensity at point P. Okay, consider according to Biosavers law we have to consider a small differential length dl at a distance z from the top of the conductor. From the top of the conductor it is the dl at the distance z. Now according to Biosavers law we know that dh equal to ideal sin theta by 4 pi r square. That formula we have to remember everywhere. Biosavers Law in the sense I dl sin theta by 4 pi r square, or simply it is the product of I into dl sin theta by inversely proportional to r square. If it is lying on z axis, hence it is dl equal to dz. I dl we can write dl equal to dz. In Cartesian coordinate systems, dl ante enti differential length in z axis lo undi kabatti manaku conductor is along z axis, hence it is dl equal to dz. Hence we can write dh equal to, in place of dl we can substitute dz. I dz sin theta by 4 pi r square. I dz sin theta by 4 pi r square. If you draw a triangle of point P located where it is located, if you draw a triangle, you can see the triangle. If you draw the triangle where the DL is located, that is R, from the origin the point P is R, and this distance is capital R with respect to DL, and this length is Z minus Z dash, that already we drawn. Here theta is this angle is theta. This angle is known as theta. From this triangle we can represent the cos theta equal to, it is the Z minus Z dash, Z dash minus Z, it is cos theta equal to adjacent side by hypotenuse is R, hence cos theta equal to Z minus Z dash by R, we can write like that. If you apply the sin theta equal to R by R, small r by capital R, therefore R equal to R by sin theta, we can write R by sin theta. Capital R equal to R by sin theta and రాయొచ్చు కదా, we can written like that. Hence from this equation R equal to R cosecant theta, we can write R by sin theta. 1 by sin theta ఏంటమ్మా, 1 by sin theta is 1 by sin theta అని ఏమని రాయొచ్చు, cosecant theta. Therefore R square equal to square on both sides. If you do square on both sides, R square cosecant square theta, make it as equation number 2. Previously we written dl, in place of dl we can written dz, that is the equation 1. Assume that it is a equation 1. This is the equation 1 and this is equation 2. If you apply the cot theta for this triangle, cot theta equal to z dash minus z by r, z dash minus z by r. If you apply the cot theta means it is 1 by tan theta. Cot theta equal to z dash minus z by r, hence z dash minus z equal to r cot theta. Differentiating with respect to theta on both sides, we can write dz equal to r minus cosecant square theta d theta, we can write. Differentiation with respect to theta on both sides, you can calculate, you can write minus dz equal to r minus cosecant square theta d theta, you can write. Therefore dz equal to ఏమవుతుంది, r cosecant square theta d theta, we can write dz equal to equation number 3. Okay, now we can write the equation 1. The equation 1 is this one, and 1 equal to dh equal to I into I dz, we can write r cosecant square theta d theta, dz is into sin theta d theta, we can write by 4 pi r square. R square can be written as r square cosecant square theta, r square cosecant square theta we written. Now cosecant square theta and this one get cancelled, r square and r get cancelled, therefore we can write dh equal to I sin theta d theta by 4 pi r. dh equal to this formula we get finally. Okay, how we are obtained? First we take in the triangle from the diagram, z dash minus z, and theta is the angle and r is the small length and capital R is the hypotenuse, and point P is located here. Here we applied from the triangle cos theta is z dash minus z by r, and sin theta is given by sin theta means adjacent opposite side by hypotenuse. Small r అనేది opposite side కదా, small r by hypotenuse is capital R. Therefore r equal to r by sin theta, we can write 1 by sin theta and cosecant theta అని రాసుకోవచ్చు, and that equal to r equal to cosecant square theta, r square equal to r square cosecant square theta అని రాసుకోవచ్చు, equation 2 that is. ఇక్కడ ఇంకోటి గుర్తుపెట్టుకోవాలి, dh ఈక్వల్ టు I dz sin theta అని రాసాం కదా, అది ఈక్వేషన్ 1. and equation 2 is r square equal to small r square cosecant square theta, that is equation 2. If you apply the cot theta for this, cot theta in the sense 1 by tan theta, 1 by tan theta, if you apply the tan theta, after that you can reciprocal of that one, it is cot theta. Z dash minus z by r, you can write like this, z dash minus z equal to r cot theta. Differentiating with respect to theta in this equation, that is dz, z dash will be minus dz equal to or cot theta differentiation enti minus cosecant square theta d theta. Therefore dz equal to minus minus both sides cancel cheseste, dz equal to r cosecant square theta d theta, that is equation number 3. If you substitute the equation 3 in equation 1, therefore dh equal to I into dz plus line substitute chesam, ఇది substitute chesam, equation 3, dz equal to r cosecant square theta d theta. Therefore we can write I sin theta d theta by 4 pi r. Now total magnetic field intensity at point P due to entire conductor we are applying, that is h bar equal to, now the limits are alpha 1 to pi minus alpha 2, why? Because the conductor along the z-axis, it is the alpha 1 and this is alpha 2, then the angle is pi minus alpha 2, it is dh bar. If you integrate dh bar over the length alpha 1 to pi minus alpha 2, then we can get total magnetic field strength at point P. Therefore h bar equal to, therefore we can write h bar equal to alpha 1 to pi minus alpha 2 dh, what we obtained previously, that is I sin theta d theta by 4 pi r. In place of dh what we derived previously, that we substituted I sin theta d theta by 4 pi r, where dh is, this is the dh we substituted, here. Now we substituted here I sin theta d theta by 4 pi r. H equal to, if you remove the 4 pi r outside and do the integration of sin theta d theta, then I by 4 pi r, we can write I by 4 pi r, sin theta integration is minus cos theta. Integration of sin theta is minus cos theta and the limits are alpha 1 to pi minus alpha 2. If you apply the limits, h equal to minus minus I by 4 pi r into cos of pi minus alpha 2, upper limit we substituted and lower limit we substituted, cos alpha 1. Therefore h bar equal to minus I by 4 pi r minus cos pi minus alpha 2, cos pi minus alpha 2 is minus cos alpha 2, cos 180 minus theta is minus cos theta, that we have to remember, minus cos alpha 1. Therefore h bar equal to I by 4 pi r cos alpha 2 plus cos alpha 1, we can write, where theta, a theta it is, the direction is a theta direction. The magnetic flux density B bar, it is the equation. By this equation we can calculate B bar, because B equal to mu h relation we are using. Therefore magnetic flux density B bar at point P is B equal to mu h, you know that. Therefore B bar equal to mu into mu naught into h bar. In h place we have substituted this equation. I by 4 pi r cos alpha 2 plus cos alpha 1 a theta. Therefore magnetic flux density B bar also. Hence like this manner they will ask the question, what is the magnetic flux density? Derive the magnetic flux density due to a conductor having finite length. This equation we have to derive. Are you understand this? A simple equation based on Biosavers law. Biosavers law is very important. And next we go for another type, that is magnetic infinite length. If the conductor is infinite length, how to calculate magnetic flux density, magnetic field intensity, that is very important. And entire these derivations one by one, it is very easy if you understand easily. If you follow that and take the paper and prepare the notes, and according to this, then you can gain the knowledge. Thank you. If you understand this, it is very easy for infinite length, because alpha 1 and alpha 2, for infinite length alpha 1 and alpha 2 becomes 0. It is very large conductor and a point P ikkada undanukunte, ఈ ఆల్మోస్ట్ జీరో యాంగిల్లో ఉన్నట్లుగా గుర్తించవచ్చు. అంటే పాయింట్ పి ఇన్ఫినిట్ లెంత్ ఇలా ఉన్నప్పుడు, సపోజ్ ఇఫ్ ఇట్ ఈస్ ఇన్ఫినిట్ లెంత్, the conductor and point P both are in parallel. For infinite conductor, suppose the conductor length is L, this is the formula we derived. If the conductor is infinite, suppose a point P and conductor both are in parallel, hence alpha in 1 equal to alpha 2 equal to 0 పెట్టేస్తే ఈ ఈక్వేషన్లో we will get for finite length. The second derivation is very simple and we have to derive this. ఇక్కడ మనం ఆల్ఫా 1 ఆల్ఫా 2 0 పెట్టామంటే ఏమవుతుంది, cos alpha 1 is 0, cos alpha 1 is, cos 0 is 1, 1 plus 1 is 2, 2 divided by 4. Let us see that for infinite length is very simple manner for infinite length. Let us see that is magnetic field intensity due to a infinite length of conductor at a point P. At a point P, what is the magnetic field intensity? For this again we have to derive the same derivation what we derived previously for finite length. For finite length having length L, a dl will be assumed similarly. If it is infinite length, the point P is located here, the dl, what is the angle making it is, for a finite length we know that mfi is I by 4 pi r cos alpha 1 plus cos alpha 2 a theta. For infinite length, alpha 1 equal to alpha 2 equal to 0. Why we are saying that? If the conductor is, we don't know what is the length, it is infinite, then point P and conductor both may be in parallel, the angle may be 0, alpha 1 alpha 2. Hence we can write alpha 1 alpha 2, if you substitute here 0, then you will get I by 4 pi r cos 0 plus cos 0, it is 1, hence it is I by 2 pi r a theta. It is very simple. The magnetic flux density B bar at any point P is B equal to mu h. Similarly what we did, B equal to mu I by 4 pi r. Simply if you know h, you can calculate B, that is B equal to I by 2 pi r, because cos 0 plus cos 0 is 2 to get cancelled, 2 and 4, that is I by 2 pi r we obtained. Okay, in this manner we can calculate easily. Next we go for magnetic field intensity due to circular conductor. That is different derivation point of view.